Let's start a little trig review here with the equation of this circle. It's called the unit circle. We're gonna use it here. So the equation of the unit circle that we're going to work with is x squared plus y squared equals 1. So that means points here on the unit circle are a distance of 1 away from the center. So 1 and 0, 0 and 1, etc. And the unit circle is going to get a lot of work done for us. In fact, this is how I develop trig in the trig class I'll be teaching Tuesday nights. If you want to sit in on it for a little while, you'll catch a more thorough development of this. But these points here on the unit circle are going to have alternate names. Let's call that angle theta, traditional angle name. And then we'll let the x and y coordinates be the sine of theta and the cosine of theta respectively. So x is the cosine of theta, y is the sine of theta, like that. And from there we can make other definitions. If we take a look at the ratio of y to x, then I get the tangent of theta. Tangent of theta is y over x. What about the reciprocal of the tangent? What's the reciprocal of the tangent called? Cotangent. Good. So the cotangent of theta would be x over y. And then we also have reciprocals of the other two functions. The reciprocal of the sine is the cosecant. So CSC, cosecant of theta, is going to be 1 over y. And finally, what's the reciprocal of the cosine? Secant of theta was 1 over x. So those are your basic trig functions, and they're going to get a lot of work done for us. Now, one of the first things I'm going to do here is use these to derive a very basic identity. There's not too many identities that I'm going to ask you that you know, just flat out know, but this is one of them. And not only should you know it, but you should know how to manipulate it. So let's start by recalling this definition that cosine of theta is x. So this is really cosine of theta quantity squared plus sine of theta quantity squared equals 1. And typically, we don't write it like this. Typically what we'll do is we'll use different notation. When we're squaring the whole thing, I'm going to put the square here. Cosine squared of theta. So these mean the same thing. And this is the most basic identity that you have when you're working with trig. Right here. It's called the Pythagorean Theorem. Now there's other versions of the Pythagorean Theorem that you can get from this. And it's handy to be able to manipulate the Pythagorean Theorem. So what I'd like for you is to be able to memorize just one identity. Just one, and then get the other ones as you need them. For instance, if I wanted an identity for the sine of theta, or sine squared anyways, sine squared of theta equals 1 minus cosine squared of theta. So now I got an identity for sine squared. And of course I could take the square root to solve and get sine by itself. What else could I do? Well, let's go back to this one right here. Cosine squared of theta plus sine squared of theta equals 1. Sometimes you're going to run into the need for other trigonometric identities that involve things like the tangent. Now the tangent, as we know, is y over x, but it's also sine over cosine. So that's sine of theta divided by cosine of theta. Oh man, if I had feelings they'd be hurt. Cosine squared of theta, cosine squared of theta, cosine squared of theta. I'm going to divide everything through by cosine squared of theta to get a new identity. Because what's sine over cosine? Sine over cosine is tangent. So what's sine squared over cosine squared going to be? Tangent squared. Over here, cosine squared divided by cosine squared, that's just a 1. How about the right-hand side? What's the right-hand side? Secant squared. So you've got another identity. And the goal here, because you're going to be hit with so many things, the goal here is to not memorize more than you really need to. I've been teaching this stuff since 19 mumble mumble, and I still don't have these things memorized. Whenever I need them, I just derive them. I just say, okay, I need a cosine squared identity, or I need a tangent squared identity, and I manipulate this. But I don't have these things memorized. Certainly I've had the opportunity. It's just not worth my mental effort. Why don't you go back to this identity and divide everything through by sine squared. See what identity you can come up with. Let's see. Fonts here. What identity do we get when we divide everything through by sine squared? Perfect. Cotangent squared of theta plus 1 equals cosecant squared of theta. So again, you're getting more identities pretty much for free. You don't have to really do too much. And I'm hoping that it's going to be easier than memorizing these things. I mean, you can. Whatever works, you know. All right, so there's a few basic identities. There's a few more that we'll need, but as we need them, I'll introduce them. These are stuff that I just hope and expect you to know. Let's move down to right triangle trigonometry here. So for right triangles only, what do I mean by right triangle? Yeah, a right triangle has a 90-degree angle. So right triangle has a 90-degree angle. For right triangles only, then you can do some other stuff in terms of thinking and working with your trigonometric definitions. So a famous acronym is this one. Yeah. A lot of you guys are ahead of me on this one. Sohcahtoa. All right. So let's define a few things first. X here, relative to theta, r here and y here. R's, the radius. We also think of it as the what? Hypotenuse. And then, of course, y would be the opposite side. And x is the adjacent side. I want to be clear, though, that this stuff doesn't work if you're doing anything other than a right triangle. It just doesn't work. Let's take a look at an extreme example. An equilateral triangle, a triangle in which all three sides are the same. It's clear what the opposite side is, but what's the hypotenuse and what's the adjacent side? Yeah, they're both the same. There's no real good way to define which one would be which. So this idea of Sohcahtoa only works for right triangles. So sine is the opposite over the adjacent. Cosine, well, figure it out. A and H. Wait, opposite over hypotenuse. My bad. Ooh, you guys should have been all over me on that one. There's a chance to prove me wrong. Adjacent over hypotenuse. And the tangent is opposite over adjacent. All right. So those are some of your basic trig functions, and a good way to work with these when you're working with right triangles. Now, quite often you're going to be working with right triangles, but certainly more often than that, you're going to be working with special angles on the unit circle. So I've given you a unit circle, kind of partially filled in with angles not only in degrees but in radians. What you're going to need to be able to do is recall the x and y coordinates that go around this unit circle. So to help you in that, let me show you a little pattern that you might find useful. And it's this. So let's write down the square root of 4 over 2, square root of 3 over 2. Can anyone predict the next one? Square root of 2 over 2, 1 over 2, and 0 over 2. So is that an easy pattern to follow so far? Now, 3 of these will simplify. The first one is a 1. The second and third one don't simplify, but the fourth one does. So it's these points that are going to help us determine the points on the unit circle, special points. So let's figure that out. Well, we'll start out on the x-axis here, and the x-coordinate here is a 1. And then I move up to 30 degrees, and the x-coordinate is square root of 3 over 2. And then the x-coordinate at 45 degrees is square root of 2 over 2. And then 1/2, and finally 0. And so those are your x-coordinates. What do you think you're going to do for the y-coordinates? Yeah, you're just going to do the same pattern going down. Start at the top. 1, square root of 3 over 2, square root of 2 over 2, 1/2, and 0. And boom, suddenly you've got all your coordinates of your special angles in the first quadrant. So, nice. But that leaves 3 quadrants undetermined. How am I going to get the angle over here, for instance? What are the coordinates there? Yes, you're going to use a symmetry. Which coordinate is going to change signs here? The x-coordinate. So this one's going to be negative 3 over 2 and 1/2. Or negative root 3 over 2 and 1/2. And likewise with all the rest of these. How about if I move down into the third quadrant? Yeah, they're both negative. Good. So negative square root of 3 over 2 and negative 1/2. Now moving over into the fourth quadrant, you've got a couple different choices. You could change the x-coordinate, make it positive, or you could drop down from here and make the y-coordinate negative. But either way, the coordinates here are square root of 3 over 2 and negative 1/2. Nice. Now overall, in these quadrants, there is a little pattern here that we're going to see when we start working with our sine, cosine, and tangent values. Everything, all 6 of your basic trig functions are going to be positive in that quadrant, so all of them. In the second quadrant, your y-coordinate's positive and your x-coordinate's negative. So anything that involves just the y-coordinate, which would be your sine and your cosecant, those are going to be positive. Anything that involves an x-coordinate is going to be negative. So just the sine functions, sine and its reciprocal, are going to be positive here. Is there anything going to be positive down here? Tangent and cotangent. Because you're going to have a negative divided by a negative, which actually gives you a positive product. So all of them, sine, tangent. What's the last one here? cosine. The x-coordinate is positive in the fourth quadrant, so that's going to be the function and its reciprocal are going to be positive. Now, there's a great little mnemonic here. All students take calc. Yeah, there you go. All students take calc. Reminds you of what's positive and where. So let's apply this to finding some exact values. Quite often on exams, I'm going to be asking for exact values. So, for example, sine of 2 pi over 3. All right, so you're going to have to be able to manipulate things a little bit. 2 pi over 3 is going to be the reflection of this one. So its coordinates are going to be negative 1/2 and square root of 3 over 2. What I'll probably do, maybe on the first test, is give you a blank unit circle. If you want to fill it in, if you need to fill it in, great. If you don't, that's fine too. But what would be the sine of root 2 over, or excuse me, 2 pi over 3? Yeah, I can just kind of give the answer. Thank you. Root 3 over 2. Now, if you can remember it from, your angles here and stuff like that, that's probably ideal. I will talk about a couple other possibilities. Let's do a few more here. Cosine of 5 pi over 4. Cosine of 11 pi over 6. Tangent of 5 pi over 4. Cosine of 7 pi over 6. And let's also do the cosecant of 11 pi over 6. And I'll do a couple examples here to kind of help you out, but I want you to try a few as well. Keep in mind we're going to be looking for exact values. And I will go through on a calculator and discuss with you a little bit on finding exact values. So let's start up here with the tangent. One way to think of the tangent is that it's the sine over the cosine. So that's sine of 5 pi over 4 over cosine of 5 pi over 4. Close. Root 2 over 2 and negative root 2 over 2. Yeah, and that's going to simplify to negative 1. And that's something actually special about your multiples of 45-degree angles. Pi over 4. Did I get these backwards? Let's see. No, let's see. 5 pi over 4. Yeah, that's quadrant 3. Oh, they'll both be negative, yeah. So it'll be positive. Thank you. Let's see, where I lost my train of thought. Let's just do a different one then. So let's move down to, let's see. Well, the cosine of 11 pi over 6, we'll do kind of a friendlier one there for a moment. 11 pi over 6, all we need is the x-coordinate at that point. So it's just root 3 over 2. Let me add one more to the mix here. Secant of 7 pi over 6. And it dovetails nicely with this one here. So I'm going to give you a minute. Help each other out. Mimi and I will walk around, try and help you out. But try and find exact values for each of these trigonometric functions. on this? Anyone need a little guidance finding these things?
Under 18.
About 20,000 steps a day.
What's that?
20,000 steps.
That's a lot. A lot of stuff.
I'm a contractor, you know, and I work at
Oh, okay.
schools and whatnot, so
Just always walking? All right.
always.
Actually, Kenny, the Seekers, I went for a bike ride this morning. That piled up a few steps. I don't know why it logs them, but it does. Okay. So, could. Let's take a look at these. Actually, I guess we kind of already did this one, right? This one is negative root 2 over 2. Cosine of 7 pi over 6. What's that one going to equal? Negative root 3 over 2. For the cosecant, what you can do is think of that as 1 over the sine of 11 pi over 6. What's the sine of 11 pi over 6? Negative 1/2. Please don't leave it like that. I don't think it's much to ask you to simplify that. What do you get? Negative 2. And last but not least, let's work with the secant here. Of course, that's the reciprocal of the cosine. So that's 1 over the cosine of 7 pi over 6. And, you know, I'm a little bit hesitant to really say what I want in terms of simplifying this. Here's what you're going to see in the book. They're first of all going to do the reciprocal, so it's going to be negative 2 over root 3. But they're not going to leave well enough alone there. They're going to rationalize it, right? So how do we rationalize it? Yeah, multiply by root 3 over root 3, so we get negative 2 square roots of 3 over the square root of 9, which is 3. So that's what you're going to see when you look in the book. Now, for a couple of these, they're so common that they come up so often, you can kind of work your way around things a little bit. For like cosine of 5 pi over 4, these two values, square root of 3 over 2 and square root of 2 over 2, one way you can work around this a little bit is to memorize, at least be familiar with and recognize these values. So that when you see them, you say, oh, okay, that's square root of 2 over 2. So if you have your calculators, you can take out your calculators. And of course, in this, you're going to need to be in radian mode. Calculus is done in radians. So let's see. My new fancy one is in radian mode. If I hit sine of, say, let's see, sine of 5 pi divided by 4, I get the decimal value for square root of 2 over 2. But, you know, at least I don't have to draw a unit circle and do that whole pattern, etc., and figure out that, oh, I'm looking at negative root 2 over 2. So your calculator can help you out. I'm not trying to make you learn all these trig values all over the place again, but more often than not, I will be looking for exact values. Now, most of us are pretty comfortable with the idea of a degree. The idea of radian doesn't resonate so well with us. So let's practice converting. And sometimes it's easier to think in degrees and then convert to radians as opposed to something else. So let's start with this idea, and that is that once around the circle in degrees is 360. What's once around the circle in terms of radians? 2 pi. So if I divide both sides by 2, that means 180 degrees is equal to pi. And it's this conversion factor that we can use to go from one to the other. So if I had, say, 330 degrees and I wanted to convert that to radians, well, unless you got a nice little chart there, maybe you don't remember exactly what that is. So here's the trick. We're going to multiply by 1. We're going to multiply by 1. Now, multiplying by 1 doesn't change anything. If your boss multiplied your salary by 1, you're not going to suddenly put them on your Christmas card list. All right? It's not going to make a difference, right? So how are we going to multiply by 1? We're going to multiply by 1 in a special form. 180 going into pi. Now, the units that you want to cancel go in the denominator. So you can cancel here like that. And you're left simplifying 330 divided by 180. And then throw in the pi. Now let me make this even easier for you. I'm assuming that you have a graphing calculator. 330 divided by 180 gives you a decimal value. But if you hit the second key, or is it the math? If you hit the math key, hit the math key, then press enter twice, you get a nice fraction. There you go. 11 over 6. So it's 11 over 6 pi is the angle that you're dealing with. 11 pi over 6. In the other direction, if I have an angle, say like 7 pi over 6, and I want to convert this to degrees, I'm still going to use this ratio. But this time I'm going to use its reciprocal, because the units that I want to cancel out are the pi's, the radians. 180 degrees divided by pi. Pi cancels right away. And then I guess the thing that I would do next is cancel 6 into 180. I'm left with 7 times 30 degrees, 210 degrees. So a quick little back and forth between radians and degrees. Now we spent a little time earlier today looking at inverse functions. Trigonometric functions also have inverses, so let's talk about those for a little bit. So inverse trig functions. Typically, we think of sine of theta is equaling the y-coordinate of a point on the unit circle. But you could undo this relationship. You could solve for theta. So theta equals the sine inverse of y, represents an angle between negative pi over 2 and pi over 2, whose sine is y. So the angle in this interval, negative pi over 2 to pi over 2, whose sine equals y. Likewise, you can have the cosine of theta. Let me give you a quick example of this before I do the cosine. So theta could be the sine inverse of 1/2. So what this is, it's the angle whose sine is 1/2. No, it's another one close to that though. So in this case, it would equal 45 degrees, or better yet, in calculus that would be pi over 4. 6, yeah. Somebody said 4. You know what? Thank you. 30 and pi over 6. You know, somebody said 45, and then I said no, and whatever. All right, so let's take a look at cosine. Cosine of theta is your x-coordinate. Cosine also has an inverse. Theta equals a cosine inverse of x is going to be an angle, is the angle in 0 to pi with cosine of theta equal to x. So Again, kind of an example. If theta is the cosine inverse of 1/2, what you're looking for is the angle whose cosine is 1/2. Now it has to be something in the first quadrant because it's positive. What angle in the first quadrant? Yeah, so it'd be 60 degrees or pi over 3. And all your functions have inverses. We make these restrictions so that the inverses are actually functions. And we use this stuff to help solve trigonometric equations. And with the little bit of time left that I have, I'm going to solve a couple trigonometric equations. So, 2. Let's take a look at 2 sine of theta cosine of theta plus cosine of theta equals 0. Now this is kind of a friendly one to warm up with because we've got 0 on one side. What we'll do is we'll borrow a trick from our algebra experience and do a little factoring and use the principle of zero products. I'll factor out the cosine. That leaves behind 2 sine of theta plus 1 equals 0. Now what does that help? Well, it means one of two things. In order for this times this to equal 0, one of those two things had to be 0. Either cosine of theta was 0 or 2 sine of theta plus 1 is equal to 0. So, all right, that means 2 sine of theta equals negative 1, or sine of theta equals negative 1/2. Now here's where your inverse trig function comes into play. One way to solve this is to take the inverse sine. Now most of us wouldn't recognize the decimal value that we get out of our calculator if we did it here, because it's going to be in radians. But if you wanted to convert from radians or from degrees to radians, then we'll be okay. So if you were to take out your calculator, you change the mode to be degrees. So that way we'll actually recognize our answer when we see it. And then I'll do second and then the sine function, second sine of negative 1/2. Make sure you don't use the subtraction key to type in a negative. Use the opposite key on the bottom row of your calculator. So I get negative 30 degrees. So negative 30 degrees. There's actually another one, but negative 30 degrees is the first one you see. Negative 30 degrees is also equivalent to 330 degrees. In terms of radians, that's negative pi over 6, and this is 11 pi over 6. And you can convert that the way we did earlier. What angle has a cosine of 0? Where on the unit circle is the x-coordinate equal to 0? Yeah, pi over 2. So theta equals cosine inverse of 0 should be 90 degrees. So cosine inverse of 0, 90 degrees. Again, you're going to answer in radians, but I mean, how many people would recognize, 1.57 as, oh gee, that's pi over 2? And if you can, great, but that's not me. All right, or maybe it isn't. I'm being modest, not sure. All right, 90 degrees, pi over 2. All right, last one. I think it's actually problem number 6 in your book. Two sine squared of theta minus 1 equals 0. I'm kind of at the end of my time here, so let me hurry this one up. I'm going to move the 1 to the right-hand side and then divide by 2. So we get sine squared equals 1/2. Of course, I don't really want 1/2. I don't want sine squared, I want sine. So what should I do? Yeah, take the square root. Now, taking the square root, hopefully you don't take just the positive square root. There's really 2 square roots here. And square root of 1/2 will rationalize as root 2 over 2. So there's 2 possibilities. Sine of theta equals square root of 2 over 2, or sine of theta equals negative root 2 over 2. Yeah, they're going to be 45-degree angles. You can get part of your answer by looking at your calculator if you wanted to. If you did sine inverse of the square root of 2 divided by 2, and you did that carefully, you should get 45 degrees. 45 degrees is pi over 4. Here you would also get another one, which would be negative pi over 4. We're going to call that 3 pi over 4. Yeah, man, my trig is off this morning. Thank you. 7 pi over 4. Now that's not all in terms of the possibilities here. There's really a couple more possibilities, other places where this is true. You can see that by looking at the unit circle. So we had a 45-degree angle, pi over 4. We had a solution at root 2 over 2. But where else is there going to be a y-coordinate at root 2 over 2? What other angle? 3 pi over 4. And similarly speaking, we had a solution down here in the 4th quadrant, negative root 2 over 2. And it has, again, parallel solutions. So 7 pi over 4 and 5 pi over 4 are both going to be solutions on that one. All right, I'm out of time here. Let me suggest a couple problems for homework. So I suggest you fill in the rest of your unit circle. Find the inverse of these functions and come up with 2 solutions, just like we were finishing up with last right here. Here's a trigonometric equation that you can try and solve, a couple trigonometric equations, and then here's the associated answers. So practice with these, and if you have some problems with your trig or anything else, let me know. You also have an SI that'll be available to get some help, but certainly one of the bigger challenges that people run into in this course is working with their trig. So good luck. Have a great holiday weekend. See ya. Yes, probably a good idea.